it's a recap of lambda expressions, and we'll see one special feature of lambda expressions. Okay, so this will be like the last part of the recap of lambda. It's basically going to be about lambda expressions and closures. So we'll touch upon closures, and we'll review lambda expressions, and basically we'll also have a look at, we'll recap variables. Okay, so that's what we're going to do this class. So we will do a quick recap of what we had covered earlier. So functions we can provide. We saw how we can provide functions as data. All right, and yeah. So again, this is how do you say it? Quite so passing around functions is something very common in Lisp. All right, and the lambda expression is basically it separates out the function name from the definition. All right, so basically you can say that lambda expressions helps you to ignore the function name because it doesn't have any name. So the lambda expression is actually just a definition, but the definition itself can be plugged into wherever you put in a name. All right, so you can pass it as it helps you to make your code neater in one thing, and there are other applications for it. Okay, but yeah, so basically you saw how we can, even if you name it, you can actually get back the function object and you can pass it around as data. Okay, so function is the operator, is a special operator that allows you to extract the function object from the name. Okay, so basically internally Lisp stores the function as a function object. When you define a function, it stores these as a function object, and that object is returned when you call function. Right, and in order to, once you get that function, there are two functions. This is a special operator actually. Okay, so it is not a, when you use function, you are using a special operator which does special operators. There are a few of them in Lisp, in common Lisp, and they have some standard definitions, and they are not they are not like, they do not have to follow the function call form. The function call form is the standard way of defining and invoking functions. So func call is a standard function. I mean, it behaves like a normal function, whereas special operators have a different way of doing things, right? So we had looked at this plot function earlier, and so we had a look at this plot function. So plot, and then also defined diff one. Right, and then we did this plot. I can do it like plot of hash. And then you can also use this to this thing. You can provide a thing. So what's happening here is basically any doubts here so far? So this was the function and func call operator. All right. So what's happening here is this function is getting passed around as an object. The object of that definition is passed around into the function, and the function is then called with the func call thing. So the reason of having this roundabout way, you could have just done fni. Okay, but you cannot. So it's like yeah. Could you do fni? It's actually yeah, we don't know if fni would work because it's a function object. All right. Yeah, so this is the way to pass around things. So you could try it out actually. Let's just try this out. Okay, what would happen if we just remove this? Okay. what would be the error that you get? Okay, that's the question that we need to see. Of course, if you pass just the square, what does it say? Variable square has no value, because inside that function it is not defined, right? You have to define it inside the function. That's inside that scope, I guess it's not considered to be a function. So, but outside you can of course say square 1. You can say that, but inside the function it is not defined. So one way would be to, yeah, so you get the point, right? So that's why you cannot do this type of thing. And also I don't know if you can, a variable, this would be a variable actually, right? So it's passing around variables. So the point here is that the function object, these are actually, if you go back to functions, these are all variables, okay? And they're variables to objects. But usually you, this is going more into the internals of Lisp. So the way this thing would be bound, it doesn't allow you to put it as a function here. So variable square has no value, okay? So it doesn't take in the binding. It depends on the internals of that Lisp thing. So if you want to pass around functions, this is what we see that we have to do it this way, or you can use apply. All right. So the same thing above, I could have done apply function I. Okay. So that's another way of defining it. Instead of two ways of, you have to pass around. So functions we have seen that you have to pass it around as an object. Okay. So and once you pass it around as an object, the way to invoke it is by either doing this my apply. So pass the object out and okay, R2. So what you have to do here is, the reason for this is, how do I rectify this? So basically we are going through this. So we saw this function call, and I was just trying to see how we can pass around functions. So the way to pass around it, we saw the normal flow. I mean the book provides this option that you can pass around this object like this. Okay. So if you want to call, because this depends on the binding that takes place. Okay. So how the objects are bound, these are variables. So these variables are bound to the objects, but those objects you cannot call it like this. Okay, you cannot put an fn and call it directly. So you have to go about by using this fun call. Fun call will take this object and then it'll apply it on the arguments, or you could use apply. So that is so that's something we saw, and so we also saw apply. You can also use apply, and the context of apply is that let's say you are providing you don't want to take out, if you're, it's like first of all, first thing is convenience, because you may not know exactly what parameters this function takes. So I don't want to specify it, all of it in a line, okay, one by one, and I want to have, I know the function, let's say I know the function name, or even the function name could be provided as input, and I don't know what the arguments it takes. So that could just come in as a list, provided as a list, and you have one way of just calling it. So it would just be called like this, all right. And the plot data could itself have a function inside it. And apply is also quite flexible in the way it accepts its arguments. So the first thing has to be a function, and the arguments to this function could be packed or unpacked. Okay, you can unpack some of the arguments, and you can put in some of the arguments in the list. But of course, they will be sequential, in the sense that you can't, it depends on the arguments for this function, how it is, what does it expect. Accordingly, you have to provide the input to it. So this could be, accepting optional or optional and keyword arguments and rest arguments. So as per that definition, that will dictate what type of input you can provide after that, the second arguments. And it's the same thing for fun call. All right. Only thing here, you have flexibility in the way you can provide data to the function. Then we had a look at lambda expressions. So lambda expressions is basically taking that concept of segregating the name from the definition to the next level. So here what happens is you don't need the name at all. You just see the lambda expression by what it does. Okay, and here we're just taking double. So we are taking the power. Okay, so you don't have to even define this thing. So one aspect of one advantage of doing that is that it becomes clearer. You can see especially for things that are shorter. Okay, you can just see that it's quite clear what it is being doing. You don't care about the name. You don't have to name it also. The name is by what it does. So we can just provide it here, and it's quite clear that since it's a one-liner function, you can see that it just takes the double of that. So this function is a function that doubles things. So yeah, we had one. We see that it's just 1, 2, 3, 4, 5. But the moment you double it, you can see that I hope this makes things also clear that what does a function do. We can also do 3 times, right? So you have some functionality, intrinsic functionality, but depending on the function that you provide, that thing the output varies. Okay, so that's the point of a higher order function. So you have a core functionality that you have captured in plot, and you say that okay, I'm open to get any function that takes one argument and returns some value, and that value will determine how I behave. So it could be like this, it could be doubled, it could be tripled. All right, but more or less you will get some kind of you'll get this type of increasing sequence of stars. That's what this function does, right? And another example of a higher function is generic sorting function, which would take integers, numbers, and it would also take more complex objects and compute for you the result, which is basically to sort as per some according to some notion of order. So that's how you make things generic. All right, so you have a basic functionality, and you allow some functions to dictate how things can be modified at runtime. Okay, so that's clear now. So I hope you are comfortable with lambda expressions and higher order functions. So both concepts are covered with this, and so far it has been covered. And what about lambda? Lambda expressions is you can think of it as a special kind of function name. Wherever you can use a name, you can plug in a lambda expression. All right. So here we use this hash quote, and then we put in the name before. So instead of that, what you can do is plot hash quote square 151, right? This is what we did. We also had a function called square 5. Okay. Now instead of that square, you can actually plug in the lambda expression there. I showed you for 2x. So you don't even have to define. One thing is you don't even have to define. For one-time usage, you can just create it on the fly. You can type it in on the fly, and so it creates things and it discards it when it doesn't need it. All right. So that is the advantage, and also you don't have to spend time. You don't have to create an extra object, or you don't have to define it separately. You can do it when you need it. All right. That is one thing, and you also don't have to think of a name for it. All right. You can just use it where you need it, and it's also clear if it is as short as this. It's quite clear what it's doing. You don't have to go and refer that function. So there are some advantages here, and of course you can also you have to be careful because it's not very readable, at least for the beginners. In the initial stages, it's not very clear, right? Sometimes it can get really so you have to be quite judicious about when you want to use it. This is a very good case where it saves in terms of timing and writing an extra lines of code which would not be necessary here. And it's also readable, much more readable than having to define square x or double x and then having to look up what that double x actually does. So that's the advantage of, there are some features of lambda expressions. Coming back to this, so we can do square of 5. We can also replace that. So see the square, actually wherever, so you use square here, and it was preceded by hash quote. So you can just plug in that thing instead of the name, but it has to be it's an expression. Okay, so it has to be in this form. Lambda is like a keyword, and you give in the arguments and you specify whatever you have to say. You can write in arbitrary functions. Every function can be rewritten as a lambda form. All right. So because it's just instead of defun, you can use lambda wherever, but the disadvantage is you have to define it every time you use it. So if you are using it in many places, uh, and if the function is more than 2 or 3 lines, then it's a little bit cumbersome if you're having many places where you're using it. So that time it makes sense to define a function name. But if it is small and you're not using it too many times, then it's easier to define it as such. Okay, so there are advantages and disadvantages in terms of managing the code and managing the readability. Okay, but in terms of how you can use it, it's basically you use it as you would use a function name. Wherever you use a function name, you can usually use the lambda expression. This is the you have to close it properly, and then you can say phi. It'll give you the same result. So name here what happens is the name itself directly describes what the function does. Okay, so the lambda expression is not just a name. It is used as a name, but the name itself is the definition. Now we come do a recap of variables. All right. So we saw that there are two types of variables, which are lexical and dynamic. So they are name places. Just a recap. We went through this variables thing. So in common Lisp, variables are name places that can hold values. They're dynamically typed, so you don't have to specify the type here. Values carry the type information, and this values will propagate that information, and the types are checked at runtime, and types are errors are detected at runtime. So it's completely dynamically typed. So you cannot specify a type also in the when you're defining the function or when you're writing the program. This will completely depend on how you use it. At the function application stage, you will do the type checking. But it's strongly typed because all type errors will be detected, and values are references to objects. Okay. So this we had this is a short overview, and recall binding forms. What is a binding forms? What they do is they introduce new variables. So we had a look at functions, let star, do times, and so on. So what is a binding? It's a runtime manifestation. It's like it binds the function definition you would have defined it, and when you call it, it will do the binding behind the scenes. All right, and so that's what we had a look at it here. So one question that I had to ask here is this thing. So yeah, so the binding will happen when you call it. This is the definition, right? So what is the how do I rectify this code? This actually has to do more with apply. Okay, apply syntax. Why does this not work? Right? How do I make this thing work? This is not working actually. So what is the thing that is missing here? The definition. So this is the definition. All right. This is the definition, and this is the place where I'm using it. What happens is that the definition is stored internally. All right. When I do the application, this basically internally this thing gets mapped to this. Okay, the binding takes place, and they are associated. So these are all what parameters are these? Anyone? What type of parameters are these? So this is the function, right? So what are the parameters for my apply plot? So this is a binding form actually, right? This thing is a binding form because it's a function definition. It's a function definition binds it's a binding form because it starts at some place. Okay, and all of these are it is within the scope that these guys are bound to this. So at application stage, so yeah, what are the parameters? This is my function. Okay, let's just restrict ourselves to this function. So how many parameters does my apply plot take? What are the parameters to my apply plot? The variable names, the parameters. Have a look at this. There are 3 or 4? How many are there? So that's why you have to sometimes see things as a S expression, symbolic expression. All right. So this is a symbolic expression, right? So when you see this as so I had this question actually, F1 and this, or let's just say my func. All right. Is this a valid S expression? Let's do it this way. Is this a valid S expression, symbolic expression? What type of parameter are they? So we have 4 types of parameters, right? There are 4 parameters to this function, but as Hari said, we have 4 types of parameters. One is required, optional, rest, and keyword. All of them are required because we don't have a specifier. This is called as this is a specifier, optional. It specifies what thing is. So if you have optional, everything after that, the things that are after that will be optional. And if it is rest, after that you follow rest and AB, and then you have key. So this is the way to do it. If you want to specify all of them, define f of this, you would do it this way. First you would write in the required arguments, and then you would specify the optional arguments, and then you have to specify the rest, and you have to specify the keys. Okay, so far, but I did not confuse you, because I did not confuse you in the sense, what I want you to guys to do first is to be able to combine required with optional, and then required with rest. Would this be a valid definition? Right? Yeah. So anyhow, so I want to combine. So required is without any definition. So required is without any specifier. So there is no specifier in the parameter list. So the specifier that specifies what the next what type of it. If you don't have a specifier, it is required. Okay, those are all required arguments. So you cannot skip them. So you have to provide 4 arguments. Okay. Now what those 4 arguments are? If I provide something which doesn't make sense, then it would throw an error. Okay, it's like say if I put func1, okay, 151, I don't have it defined, so it will throw me an error. Even though the rest of the parameters are done, this thing is not defined. That's the second part of things. Okay, but the first part is that the type should be like the application should match the definition, if in some sense. Okay, here the first part of it is the number of thing you provide. So for example, this is also not a valid function application, though I'm giving you a valid function name. This will not go through because it's too few arguments. This is always there. All right. So my question now is more of, what is it that I have to do to make this work? Like this. So I'm using plot. Internally uses func call. Can I do it with apply? That's my question. Again, I should be able to do with apply, right? Because apply is more flexible. But what am I missing here in this definition? So earlier what I was trying to do is I was trying to put an fn in the first. Okay, that is not going to work because that we have to get more. I guess that doesn't work. It's not allowed in Lisp because yeah, that's not a valid way to call a function. Okay, because that will depend on the bindings that are taking place. Okay, and so it's not going to be possible to do it. Yeah, and we'll have to see technically why it's not possible, but that we'll go as I understand the interpreter better. Okay, but there are 2 ways. We can do func call, we can apply. All right. So how do I make this work? How do I make it work with apply? Because just replacing func call with apply doesn't seem to be working. Okay. There are I think a few ways to do it, but basically apply is more general than func call. So what should I do to make it work? What's lacking here? Does the structure of this code do you find it difficult to understand it? Because I broke down the structure to you last time. I explained what loop repeat does and what loop for does. Okay. and the point of having this, what is the need for having a function inside this? It just gives you the value that how many times you have to repeat for. So that is a function of the input, the function that you provide in the input. That will determine the number of times each line is printed. So this is more of a question of, so the binding takes place, the function is bound to this, and the min max step are all fine, and this is the I that is being made. How do I make this? Is basically you have to make this function call. Instead of func call, you're using apply. How do I make, what is missing here? Because it expects a list at the end, okay? So you can do it this way. Now if I do my apply plot, it will actually work, it should work, because I am missing one thing here, right? This works, get it? Another way to define it is by basically for apply, it requires a list. The last thing should be a list. Yeah, or maybe this may not work because of, yeah, it's not a R2. So the way to do this would be, you can make a list out of it, right? And then apply this, it should work. Clear? So wherever you have a func call, you should be able to, it is possible to replace it with apply. Apply is more general than func call. Wherever you use func call, you should be able to use apply for it, okay? So coming back to the binding forms, so the binding forms introduce new variables, all right? So whenever we have defined this function call, and here we're applying it. So the function definition does the binding here. It binds the square to the first thing, and these are required form. If you have optional, it will do the binding requires some amount of, it's also like, you know, it also has to do some kind of matching, pattern matching and other things, all right? So it has some process of matching the arguments to the variables, all right? And so the rules, there are some rules, and those rules determine how they get matched. So for required, it's quite easy. The first thing is matched to the first one. The first, I mean, as this is positional, so it's just like one-to-one mapping. So first one has, each of these will have values, and you have to have, and they will be matched in the first as per the position. The first guy will be matched to the first argument, second will be the second, which is the normal flow. But when you have positional and when you have just one more, it makes things a little bit more interesting, or more a little bit more flexible as well as it makes it a bit more work to do. Okay, it's more not you know, straightforward, because it's just a one-to-one. When it's optional, you might have it, you may not have it, which is also quite easier to think of. But when you have rest, I mean, so combining required with one more parameter should be very comfortable for you guys to think of it, to deal with it, all right? So that's the first step. And then after that, we can see how we can combine multiple parameter types, okay? But all of this has to be done by the interpreter, and it has ways of doing it, all right? Some things may not be as intuitive as you might expect, may not be as you would have expected. It has some, you know, things we have not looked at that. That's why I'm mentioning this to you, okay? But simple, this is very simple. So it does the binding, and then it goes into this apply. Apply takes that function, and it takes this, it needs a list at the end, okay? So this thing is actually, it is you can think of this as taking a rest argument, okay? All right, so the way it does it is, it's quite clear. If you understood rest, that rest is what is being used in apply, okay? So you can see that apply needs a rest, so that's why you need a list there. And this is how it ties up with the parameter types that we had taken up, okay? So you cannot apply, you cannot do this thing here without you cannot just put I, because apply is it's quite clear from the way we are using it that it is actually taking a rest argument, okay? So rest argument you have, if you do, and it is doing some check internally, and it's processing that rest argument. So it requires that rest argument. So you have to put a list at the end, okay? because it allows you to have arbitrary it allows you to apply with the list, and also gives you a lot of flexibility. But at the same time, one thing it definitely requires is that the last argument has to be a list. Otherwise, this will not work. Okay, so that's about apply, and this is about a little bit about bindings also. Bindings with function of parameters. So these function parameters will hold object references. All right, and we saw the setf and macro and setcube operator. So both types of variables, lexical or dynamic, they use two slightly different scoping mechanisms. We had covered this also earlier. And in both, the scope is determined by the binding form. Okay, I had mentioned this to you. All right. So we had an example earlier. Everybody remembers this, right? And you guys said that's okay. It's quite straightforward. Okay. So this is the normal flow of, more or less, this is quite clear what's happening here. So if I say foo1, right? This is the normal flow lexical scoping kind of mechanism, wherein the x, so this 1 gets bound to x, and this is the x that is, the value is the value that is coming from outside. This is 1, which gets bound to the at the function application stage. Then this gets overridden. This binding overrides that thing. All right. Now we have that in this thing we have that x is 2, because this guy shadows the outer argument, and then another nesting inside that let. So we had set it as 3, and this guy shadows that, and then when it comes out, this gets closed here. So we come out, it becomes like back to 3, 2, and then it goes back to 1. So this is the normal thing. So this we postponed it because we didn't have a idea of we did not cover lambda expressions, but now we have an idea what lambda expression does. Now I'm going to use a lambda expression here, and I'm using a setup. Okay. All right. What's happening here? Anyone? So this particular expression, it combines a lot of things. Okay, it uses let, it has lambda, and it has a substantial amount of. It covers quite a lot of things that we have done so far. Can anyone explain to me what's happening here? What does this thing return? What does this program do actually? Any idea? What does it return actually? So let's say let's understand what it returns. So you know that let returns something, right? Let will return. What will it return? Format for let is let. You do the variable binding star, and then you close it. Okay. So this variable star, can anyone identify what is the variable star in this thing? What is the variable and what is the plot body? So this again is like deconstructing things, right? You start off with the form and you match it. It's called pattern matching. So there's a lot of pattern matching that goes on in Lisp. All right. So when you define a function and when you do the application, there's a matching that goes on between the function definition and the application. So the binding is actually it does the matching. It matches the arguments and it assigns some things behind the scenes. So there's a lot of pattern matching going on. Okay. So for me, what I want to know is, this is the let form. I wanted you to deconstruct this expression and explain to me what is happening here. All right. Or you either the general way of doing it is to deconstruct it. All right. To deconstruct it by expression. All right. And deconstruct it basically. Okay. Decompose the expression into its substituent parts. So when I want to look at it as a S expression, I will say that it is S1 of the form S1, S2 and S3, right? Where this is the exercise what I wanted you guys to do. See how it is relevant, because S1 is what? Let. Okay, S2 is equal to what is it, and that's what I want. Okay, if you see it as an S expression, but if you see it as a Lisp, this is also a Lisp form, which is a special operator, special form, special operator form, because let is a special operator. Okay, so the form determines the way it is evaluated. Okay, if it is a function form, we have a way of evaluating it. If it is a macro, it will have its own consequence. It will have its own way of evaluation. And if it's a function call form, that has a quite standard way of evaluating. Function call forms, each of its arguments, it should also be a Lisp form. It need not be a function call form. It has to be a Lisp form, but okay. So that's how you understand things. So that's two or three levels of abstracting out. Okay, first you need to break it down as symbolic expressions. All right, and if once you get once you're comfortable with syntactically breaking down these entities, you can then think of what form is it. Okay, and then I'm talking about what does it. I mean, I'm asking many. This particular expression has many things going on here, because you need to understand this thing first, and then we can close this. Yeah, at least you can try and understand it. Attempt at breaking at some level, right? We have done symbolic expressions, we have done Lisp forms. All right, symbolic expression helps you to deconstruct the expression. So everything in Lisp has to be a symbolic expression. All right, every Lisp form is a symbolic expression. So if you can see this as a, if you are stuck somewhere, you can always go back to symbolic expression. Okay, and you can deconstruct it, and then you can reason about it. All right, and you can say, okay, these are the parts. Okay, so similarly what I had to say was, if I say diff1 f1, right, so is this a valid symbolic expression? Forget about the code, but yeah, right. And what are the parts of it? So this was a question. So basically what happens is, this is of the type S1 S2, okay, where S1 equal to df1. It's a symbol, right? df1 is a symbol. When you want to think of a symbolic expression, it is a symbol. And S2 is f1, which is also a symbol. So hence df1 is an atom and it's a S expression. F1 is also a symbol, and hence it's a atom, which is a symbolic expression. So this whole thing is actually of the form S1 S2, where S1 is df1 and S2 is f1. Okay, this goes back. This is the mention new here in BA. Everything in Lisp has to be a symbolic expression. When you identify the parts that are a part of this, then you think, okay, what is the first part of this? What can it be? It's a special operator, a let special operator. Okay, but that's later on. First, you need to identify the parts here. So whenever you look at a symbolic expression, you can always do that splitting up. All right. So, and in fact, this same thing, diff1 f1, like this, is of the form S1 S2 S3, where S1 equal to what? df1. S2 is f1. S3 is the empty list. I have been clear to go through that and to get this right. It's very syntactic. You don't have to think anything. Don't think of the definition of df1 and all those things. Okay. When you want to consider it as a symbolic expression, you just have to break it down. Okay, you have to break it down into constituent parts. All right, it's a mechanical process. It's very mechanical. All right, and that's what the interpreter also does things. So you have to break it down into its constituent parts, and you just go through the symbolic expression. You break it down. All right, but here what I'm asking you is, yes, you can do that, and you can also think of what it is doing here. All right. Okay, I'll tell you what's going on. Okay, I'll just try to close up with this. So what's happening here is basically, let's just go back here, since Yeah, let's just do this. So we are having this setf as the instruction, okay, for this lambda form. This lambda form is a function which doesn't take any arguments. What does it do? It just takes its setf. It takes the count, and it sets count. It takes internally it takes 1 plus count, which gives you the value, and it sets the counter variable count. Okay, and inside this let expression, it is having this count 0 defined. Okay, this one expression, it uses everything. It uses the let expression. It introduces variables count. All right, and the count, it then creates a lambda function inside let expression this. So it returns for you a function. You can see this returns for you a function. Okay, and I can take that function and I can set it f here. All right, I can do the set f here. What does this do? It sets the thing f. All right, and I can set same thing to set g. Get it? All right, now the normal lexical scope, what would have happened is this count 0 is only defined inside this, right? But the moment this guy is returning for you a value, this is a function, I can then call this function f. All right, and you notice that the one, so this is how it is working. So yeah, this count is a lexical variable. Okay, we haven't discussed global variables yet. So this is a very interesting thing that's happening here. Yeah, this has everything inside it. Okay, so the scoping is what we can discuss here. Okay, what's happening here is this count is this is a lambda object. You can not only not only can you pass it as input, you can also return it as a output. Okay, so the let expression returns a function object. Okay, think about that first. So it gives you the function object. Now that function object, what am I doing? I am putting it in f. I can also put it in another variable g. Okay, but these two function objects are I guess it depends on how Lisp internally does this computation. All right, but basically it's sitting inside a let. Okay, so that count 0, it is you are, even though the let is done, it's closed, it has returned it, but it is actually it is being called in the f function. I hope that's clear. And there are two different copies actually of that thing. Okay, though let is returned, all right, it still allows you to, when you call the function f, it's you can think of it as still alive. Okay, so that count is still alive, and it increments for you the value and returns the value of count. Is it clear? This is what is known as a closure. Okay, this function is a closure. So we'll go through this a lot more. This function is called a closure because it closes over the let binding. Okay, so this is the introduction of closures. All right, we have to also go through the global variables, def parameter.